Right. Good morning, everyone. Hello. Welcome to Guru Brahma classes for JEE and NEET. We are in the chapter Chemical Equilibrium. In this session, we are going to learn about applications of equilibrium constant. Up to now, we have discussed what is equilibrium constant, what is the relation between equilibrium constant and the standard Gibbs energy change. Okay. We solved some problems on equilibrium constant. Types of equilibrium constant we have spoken or we have discussed. In this session, what we are going to learn is applications of equilibrium constant. By looking at the equilibrium constant, what we can decide for a given reversible reaction. So let us see that. Let's start. So applications. The first application is what? Predicting the extent of the reaction. What is the meaning of extent of the reaction? Here, extent means how much reaction has been completed, how far the reaction has been occurred. That is the meaning of extent of the reaction. Whether the more reactants have been converted into products. So, extent of the reaction, how far the reaction is completed or happened, how far the reaction has been happened. That is called as extent of the reaction. Right? So, whether it is Kp or Kc, for a given reaction, for example, let us take A gives rise to B. A is reactant and B is product. What will you write? K equilibrium. Let us write Kc, concentration of product by concentration of reactant. Okay. So if Kc is more, if Kc is more, then what does this represent? Numerator is more and denominator is less. This describes that concentration of B is more and concentration of A is less. That means, what does that mean? Reactant A reacted more. There is very less reactant and there is more product formed. So more reaction has been completed, more reaction has occurred. Are you getting this? What does Kc more value represents? More value represents that product concentration is more and reactant concentration is less. What does that mean? That means that reactant has participated in the reaction more amount of reactant has been completed so that it is converted into product. Less amount of reactant is present. That is the meaning of more K value, K equilibrium. Then if Kc is less, what does that mean? B is less, right? Numerator is less and denominator is more. Concentration of A is more. What does that mean? Less amount of reactant has participated in the reaction. Less amount of the product is formed. The reaction happened very much less. That is the meaning. Okay. That means here Kc more the extent of the reaction. Kc less extent of the reaction. Okay. Kc more means more extent of reaction. Kc less means less extent of the reaction. Okay. So let us see here. The numerical value of equilibrium constant for a reaction indicates the extent of the reaction, how much the reaction has occurred. more or less. The magnitude of Kc, magnitude means the value of Kc, is directly proportional to the concentration of the products and inversely proportional to the concentration of reactants. This already we know. Product of the concentration of the products by product of the concentration of the reactants. That is called as what? Equilibrium constant. If Kc generally in many reactions was experimented and gave a general representation. What is given? A general value is given, and what is that? If Kc is greater than 10 power 3, if Kc is greater than 10 power 3, okay, greater than 1000, if Kc is greater than 1000, that means more Kc. What is the meaning? More Kc. More. Kc is more. What does that represent? Products predominate over reactant. Product concentration is more. B concentration is more than A. If Kc is very large, that means if Kc is, for example, if Kc is something like 10 power 7, that is very large. Kc is very large, then the reaction proceed nearly to completion. Completion means almost the reaction has completed. 99.9% of the reactant has been converted into product. That is called as proceeds nearly to completion. So generally, if it is greater than 1000, we say that product concentration is greater than reactant concentration. But if Kc is very much large, then we say that the reaction has almost completed. Okay. So let us see. There is another condition. If Kc is less than 10 power minus 3, that means if Kc is less than 1 by 1000, then the reactants predominate over products. Already we have seen Kc is less. If Kc is less, B is less. Okay. And A is more. What is A? Reactant. What is B? Product. Reactant will be greater than product. Reactant will be greater than product. If Kc is very small, if Kc is very much small, the reaction proceeds rarely. That means very less amount of the reactant has been converted into product, like 0.01%. Okay, if Kc is 10 power minus 9, for example, very small. So then the reaction proceeds rarely. Proceeds rarely means, what is the meaning of that? Proceeding rarely, very less amount of the reaction has been occurred. Very less reactant, amount of the reactant has been converted into product. That is the meaning. Understood? So if Kc is in the range of 10 power minus 3 to 10 power 3, if Kc is in the range of, Kc is in the range of means, what is that meaning? 10 power minus 3 to, what is that? If this Kc is in this range, 1 by 1000 to 1000, then appreciable concentrations of both reactants and products are present. That means there will be some relation between reactants and products. Now we have seen that here if it is very large, product concentration is very much or very high when compared with reactant concentration. If Kc is very small, then we say that reactant concentration is huge when compared with that of the product concentration. But if it is in the range of 1 by 1000 to 1000, then we say that there is a comparable product concentration and reactant concentration we can compare. We can compare means if product concentration, for example, if it is taken as 0. Something 5 molar, reactant concentration, let us take it is 0.1 molar. Now there is comparison. Okay. So this, now we can say that they can be compared. That's comparable values of concentrations are present. That is here the meaning they have used. What is that? Appreciable concentrations of both reactants and products are present. So generally, if it is very large or it is very small, one of the concentration will be very high and one will be very small, very small. Are you getting this? But if it is in between 1 by 1000 to 1000, then appreciable concentrations are present for this product and reactant. Are you getting this? Right? So that is represented in the form of an arrow. Let us see. So what is this Kc? Kc extremely large, Kc negligible. If it is negligible, if Kc is negligible, that means, so 10 power minus 9 we have discussed, that is 10 power minus 9, negligible, very much less. So reaction hardly proceeds. Hardly proceed means reaction has not much started, only just 0.05%, 0.01% of reaction has been started. That's it. So if it is between 10 power minus 3 and 10 power 3, both reactants and products are present at equilibrium. Both are present in appreciable amounts, in comparable amounts. And if it is very large, like 10 power 7 or 10 power 9, reaction proceed almost to completion. That means more amount of the product is formed. So simply, if you confine this concept, what we can say that if Kc is more amount of the product is present, more reaction has occurred. If Kc is less amount of the reactants has been converted into product. That is the meaning. By looking at the equilibrium constant, we can say how much extent the reaction has happened. Okay, so this is one of the application of what equilibrium constant. Let us see next application. So this is very important. This is asked in different competitive examinations. Okay, so what is that? Predicting the direction of the reaction. What is that? Predicting the direction of the reaction. So how can we know the direction of the reaction? So direction of the reaction, to understand this, let us see this. For a reversible reaction, let us take a reaction, a reversible reaction. Reversible reaction. Reversible reaction. So reversible reaction, A is giving rise to B. Okay. A is giving rise to B. Now A is converting into B and B is also converting into A. What is the destination of a reversible reaction? Here we are speaking, what is the destination of a reversible reaction? That means reaction has started, reactant is converting into product. After the formation of certain amount of the product will be converting into reactant. Okay. Then at a certain time, you will find that rate of the forward reaction is equal to rate of the backward reaction. And that is what called as equilibrium, the state of equilibrium. What is equilibrium? It is a stage or state at which the rate of the forward reaction is equal to rate of the backward reaction. Okay, that means A, reactant A is converting into B and B is converting into A. So let us take at equilibrium, rate of RF is equal to RB. What is R? Rate. F means forward reaction. RB means rate of backward reaction. So we say that at equilibrium, rate of forward reaction is equal to rate of backward reaction. For example, let us take 5 molecules of A are converting into B. Forward reaction. Let me consider what is that? Forward reaction. 5 molecules of A are converting into B in 1 second. 1 second. Okay. In 1 second. Let us take backward reaction. What is that? Backward reaction. Backward reaction also, 5 molecules of B are converting into A in 1 second. Now, it is just taken as an example. Now we can say that the rate of forward reaction is equal to rate of backward reaction. Rate of backward reaction. And we have studied that equilibrium, chemical equilibrium is dynamic in nature. But what is the meaning of dynamic in nature? The reaction appears to be stopped at equilibrium, but both forward and backward reaction continues to take place. Both forward reaction and backward reaction continues to take place. It does not stop. That means A molecules are converting into B, B molecules are converting into A. Okay. For example, there is some change. At equilibrium, this is the situation. Okay. For example, I am speaking that there is some net change in the number of molecules. Net change in the number of molecules. For example, let me take 8 molecules of A. 8 molecules of A are converting into B, and 2 molecules of B are converting into A in 1 second. In 1 second. Now, whose rate is more? A to B is more. Does it mean that B is not converting into A? Yeah, B is also converting into A. That means products are converting into reactant. So, net rate is forward direction or backward direction? See here, backward reaction. For backward reaction, 2 molecules are converting into reactant, whereas forward reaction, 8 molecules are converting. So net rate will be, net direction will be, net rate, or we can say direction, net direction of reaction. What we can say? Net direction of reaction will be forward, because here 8 molecules. So let us understand it. 2 gets cancelled. How many molecules of A are converting into B than B to A? 6 more molecules of A are converting into B. Are you getting this? 6 more molecules are converting from A into B. So net rates or net direction of reaction is forward, because more number of A are converting into B than B to A. That means rate of forward reaction is greater than rate of backward reaction. So the net direction of the reaction will be forward. So we need to understand that here direction means both forward and backward reaction continues to take place. We are speaking about net change in the number of molecules. Net direction. Are you getting this? Okay, net direction. So what that is this direction, that is this direction, both forward and backward reaction continues to happen in a reversible reaction. Okay, we are speaking about direction means net direction. You have to understand that it is a net direction. Okay, let us see. Here for the reaction, let us take another reaction. A gives rise to B. So what do you write? You are writing Q. What is called as a reaction quotient. What is that? Reaction quotient. What is reaction quotient? Q. When it is written for a reaction which is for a reversible reaction which is not in equilibrium, where it is which is not in equilibrium state. So reaction quotient is written for a reversible reaction which is not in equilibrium state. So for the given reaction, what I can write? Q. If I say C, that represents that it is the reactants and products concentration, equilibrium, their concentrations are mentioned. What mentioned? Concentrations. When we represent concentration of reactants and products, then we write it as a QC. So concentration of B by concentration of A. This is how we represent Q. Q is what? Reaction quotient. When it is written for a reversible reaction which is not in equilibrium. Understood? Then for the same reaction, if I write Kc, I am also writing it as B by A. Concentration of B by concentration of A. Sir, looking to be similar. What is the difference between these two? Yes, there is difference. Representation is same, but there is difference. Here, when do we write Kc? We write Kc when the reversible reaction has attained equilibrium, and this B concentration and A concentrations are equilibrium concentrations. When do we write the QC? When the reaction is not, it has not attained equilibrium. It is not in equilibrium. When it is not in equilibrium, what is that? The concentration of product and concentration of reactants. So Q is written for a reaction which is not in equilibrium. Kc is written for a reaction which has already attained the equilibrium, which is in equilibrium. Understood? Okay. So that is what here it is mentioned. You see, what is reaction quotient? Reaction quotient is the ratio of molar concentration of the products to the product of molar concentration of reactants. Similar definition to that of Kc, but with each concentration term raised to the power equal to stoichiometric coefficient at any stage. What is this? This point is important. At any stage during the process of reaction. Okay. So for example, 2 moles of A react with 3 moles of B gives rise to 4 moles of C and 5 moles of D. Then what I write? QC. QC is equal to C concentration power 4, D concentration power 5 by A concentration power 2, B concentration power 3. This is very much similar to that of Kc, but these are not equilibrium concentrations. When you are writing QC, these are the concentrations at any stage of a reversible reaction. Any stage of a reversible reaction. These are not equilibrium concentrations. Are you getting this? Okay, so this is the difference between QC and Kc. When QC is greater than Kc, QC is greater than Kc. So now only we have written QC and Kc here. So let us take QC is how much? Let us take 5 for the purpose of understanding the LC. KC is how much? KC how much? Let us take 2. So is this condition satisfied? QC greater than KC. Yes, the condition is satisfied. You can also write QP greater than KP also. It doesn't matter. So C and P are written when the products and reactants, how they are represented. If they are represented in the terms of their concentration, we write Kc. If they are represented in the terms of their partial pressures, we write Kp. Okay. So Qc is greater than Kc. So Qc, which is not in equilibrium, Kc means which is in equilibrium. So Qc is greater than Kc. And we know that this point is important. The final destination of a reversible reaction is, what is its destination? To attain equilibrium. If it is not in equilibrium, after 10 seconds, after 15 minutes, after 30 minutes, whatever the time it takes, after a certain period of time, it attains equilibrium. The final destination is attaining equilibrium. Are you getting this? So now, so QC, when you write QC, what do you write for the reaction? QC is equal to product concentration by reactant concentration. For a reaction, R gives rise to P. Okay. So QC greater means, what is the meaning of product concentration greater than reactant concentration? Here greater means product concentration greater than reactant concentration. Okay. So to attain equilibrium, QC must decrease. Why it has to decrease? Because Kc is only 2. Why it has to decrease? Because Kc is only 2. If Kc is 2, then Kc means it is written for a reversible reaction at equilibrium. So if it attains equilibrium, K must be equal to 2. Now it is more. It has to decrease. Why it has to decrease? Because the final destination of a reversible reaction is to attain equilibrium. So to attain equilibrium, what happens is Q must decrease. If Q has to decrease to attain equilibrium, QC must decrease. Then if it has to decrease, what has to happen? Product concentration must decrease and reactant concentration must increase. Product concentration must decrease and reactant concentration must increase. Is it correct or not? So product concentration decreasing and reactant concentration increasing means what happens? What will be the direction of the reaction? Net direction of the reaction is reverse, backward, you see. What has to happen? Product concentration must decrease, reactant concentration must increase. When can it increase? Product has to convert into reactant. So product converting into reactant means what is the direction of that net direction of the reaction? Net direction of the reaction is backward direction. That is what here. The reaction will proceed in the direction of reactants, that is backward direction. Are you getting this? Okay. So condition you need to remember, when QC greater than KC, concept must be understood. All the things we cannot remember, but the concept we must remember. This is very much important examination point of view point. Okay. So if QC is greater than KC, this is written for a reversible reaction. The final destination of a reversible reaction is to attain equilibrium. As QC is written for a reaction which is not in equilibrium, as it has to attain equilibrium, its value must decrease. If it has to decrease, product concentration must decrease and reactant concentration must increase. If it has to happen, the reaction must move in backward direction. So the net direction of the reaction must be in backward direction. Okay, so next let us see the next one. If QC is less than KC, QC let me take 2 units, KC let me take 5 units. Okay, and we know that for a reaction, reactants gives rise to product. So QC will be product concentration by reactant concentration. As QC is less than KC, to attain equilibrium, what is that? To attain equilibrium, QC must increase. If it has to increase, product concentration must increase, right? And reactant concentration must decrease. If product concentration must increase or reactant concentration must decrease means, what is the direction of the reaction? Product must increase, reactant must decrease. That means net direction of the reaction will be forward. So the reaction will proceed in the direction of the products. So that is forward direction or forward reaction. Are you getting this? So the condition you have to remember, KC greater than QC. Forward direction. QC greater than KC, backward direction. If QC is equal to KC, both are same means, what does that mean? Reaction has attained the equilibrium. QC 2 units, KC is also 2 units, both are same. That means the reaction mixture is already at the equilibrium. Hope so you understood. This concept is very important. You must understand this concept. Okay. So let us solve a problem of this. Here let us see what is given and what is asked. There is a reaction. There is a reaction. The KC for the equilibrium reaction is given 2CO. Okay. 2CO2 gives rise to 2CO plus O2. KC is equal to 4, what is that? 6.4. 6.4 into 10 power minus 7. Okay. Predict whether the reaction will take place to left, net direction of the reaction. He is asking us a net direction of the reaction. Takes place to the left or to the right to reach equilibrium, or it remains same at equilibrium. Okay. So these are the concentrations of carbon dioxide, carbon monoxide and oxygen in the equilibrium mixture. See, in this reaction mixture, see, what are present? CO2 is present, CO is present, O2 is also present. Their concentrations are given. By looking at the concentrations, we will try to calculate Q, and already K is given, KC. So if you calculate QC and if you compare them, then we can understand that whether the reaction is happening in forward direction or backward direction, or whether the reaction is at equilibrium. See here, no units are not mentioned. No units, but already we have studied that units for Kc will be equal to. So what is the delta N for this reaction? Let us write delta N for this reaction. 2CO2 gives rise to 2CO plus O2. All are gases. All are what? Gases. As all are gases, what will you write delta N for this reaction? Delta N is equal to 2 plus 1 minus 2. So 2 plus 1 minus 2. Okay. That is equal to 3 minus 2. That is equal to 1. Then what should be the units of Kc? Kc units must be moles per liter power delta N. That is equal to, the units must be moles per liter. So we have to write, actually what we have to write, 6.4 Kc is equal to 6.4 into 10 power 7 moles per liter. But here moles per liter is not given. Why they have not given? So this is one of, so how do we take this? So this Kc is how many times to that of 1 mole per liter? How do we consider it? We are considering Kc. We are relating this Kc with 1 mole per liter. How many times this Kc is to that of 1 mole per liter? It is 6.4 into 10 power 7 times. 6.4 into 10 power 7 moles per liter is how many times to that of 1 mole per liter? How many times? 6.4 into 10 power 7 times. So simply we can also consider Kc as what? 6.4 into 10 power 7. So this is one way of understanding it. It is being considered in that way. That is the reason why what is not given, actually there should be moles per liter, but it is not given. Why it is not given means because it is related with 1 mole per liter. It is compared with 1 mole per liter. How many times it is with that of 1 mole per liter? In that way we are comparing it and we are writing. Hope so you understood. Okay. Next, let us proceed with this problem. So in solving this problem, let us solve, what did we know? Let me write Qc for A. What will you write? Qc is equal to product concentration CO power 2 into O2 by CO2 concentration power 2. That is equal to, so what is given? Carbon monoxide concentration is 3.6 into 10 power minus 4 square into O2 concentration is 2.4 into 10 power minus 3 by CO2 concentration is 5.3 into 10 power minus 2 square. And solving this, what do you get? 1.11 into 10 power minus 7. Compare now with that of Kc. Okay. So Kc how much given? This is Qc. Qc is 1.11 into 10 power minus 7. Kc is 6.4 into 10 power minus 7. So now we can say that Qc is less than Kc. Qc is less than Kc. If Qc is less than Kc, then what we have studied? Do you remember? Qc less than Kc, whether forward direction or backward direction, Kc is more, Qc is less. So if Qc is less, Qc has to increase. If Qc has to increase, then the net reaction must be in forward direction. So the reaction will be in forward direction, right side, from left to right, to the left or to the right. It is as to the right it happens. Okay. Next, let us see Qc, second one. What is that? Second, B. Again Qc, same 3 point, what is given? 2.1 into 10 power minus 2 square into O2 5.7 into 10 power minus 5 by how much? So 1.78 into 10 power minus 2 minus 1. What is that? Minus 1. Minus 1 carbon dioxide square. Then if you solve it, what you get? 7.93 into 10 power minus 7. So what is QC given? KC given? KC is equal to how much? 6.4 into 10 power minus 7. Right? So now you say QC greater than KC or KC greater than QC? QC is greater than KC. As QC is greater than KC, what reaction occurs? Backward reaction. Backward direction. The net reaction, net direction of the reaction is backward direction. Okay. Then coming to the third one. Conditions QC, that is equal to 2.4 into 10 power minus 2 square into 1.18 into 10 power minus 5 by 1.03 into 10 power minus 1 square. So on calculating this, what do we get? 6.4 into 10 power minus 7. Now what is the direction? Now we have found that QC is equal to KC. As QC is equal to KC, the reaction net direction, there will be no net direction because the reaction is already at equilibrium. The rate of forward reaction will be equal to the rate of the backward reaction. Understood? So such questions are given in JEE mains level and the NEET level of examination also. So we must understand the question that these concentrations are the concentrations of the reactants and products in the container. And by calculating QC and when you are comparing it with KC, then we will be able to understand whether QC is greater than KC or KC greater than QC or KC is equal to QC. Right? So this part of the application of KC is very important because the direction of the reversible reaction is asked in the examination. Right? Next application, third application is, what is the third application? We can calculate the equilibrium concentrations. What can be calculated? Equilibrium concentrations can be calculated. Okay. So the reaction was started with 0.1 mole each, 1 molar concentration each of carbon monoxide, water at 800 Kelvin. Kc for the reaction is given. What is that reaction? CO gaseous plus H2O gaseous gives rise to CO2 gaseous plus H2 gas. Okay, this is the reaction. And Kc is given for this reaction. How much? 4.24. What is the equilibrium concentration of CO2? So we know how to solve this problem at time t is equal to 0. The reaction has not started. The reaction was started with 0.1 molar, 0.1 molar, here also 0.1 molar. So let us consider this 0.1 molar means always let us consider in this way that the reaction is happening in a container of volume is equal to 1 liter. Then 1 molar means how many moles? 1 mole per 1 liter gives you 1 molar. So consider this, the total reaction is happening at what? In a container containing 1 liter volume. A container of 1 liter volume. Now let what is that? Let X be the degree of dissociation. Degree of dissociation. If X be the degree of dissociation, okay, so completed, how much is completed? So completed will be X molar, formed will be, and we know that 1 mole of this completes 1 mole of carbon monoxide on reaction with 1 mole of H2O. How many moles of carbon dioxide is formed? 1 and 1. If X is completed, then how much will be formed? X and X. Okay. So at equilibrium, what will be the situation? Already 0.1 is there. X is completed. It will be 0.1 minus X. Initially, at time t is equal to 0, we have 0.1 molar. So 0.1 minus X. How much carbon dioxide is formed? X. And how much hydrogen is formed? X. Then if you write Kc, then what you write for this reaction? Kc is equal to CO2 concentration into H2 concentration by CO concentration into H2O concentration. So what are these concentrations? Equilibrium concentrations. What are equilibrium concentrations of CO2? X into X by, okay, 1 minus X into, sorry, how much? 0.1 minus X. So 0.1 minus X into 0.1 minus X. Then Kc how much given? 4.24 is equal to X square by 0.1 minus X square. So square root on both sides. Then what do you get? X by, is that X by 0.1 minus X is equal to 2.059. So what is the question asked? The question asked is, what is the concentration of carbon dioxide? What is the equilibrium concentration of carbon dioxide? So what is the equilibrium concentration of carbon dioxide? If you can calculate X, then that will be the answer. So if you calculate this, what do you get? X is equal to 0.067 molar. So concentration of carbon dioxide at equilibrium is equal to 0.067 molar. So this is how, by using the equilibrium constant, see what is given here, equilibrium constant is given, and you are asked to calculate the equilibrium concentration of carbon monoxide. So by looking at the equilibrium constant, are you able to calculate the equilibrium concentration? Yes, we are able to calculate the equilibrium concentration. So that is what the third application is. What is the third application? We are able to calculate the equilibrium concentration by giving or by looking at the equilibrium constant. Understood? Hope so you understood it very well. This is all about the applications of equilibrium constant. Hope so you understood it very well. Thanks for watching. We shall meet in the next class with a new topic. Thank you very much.